Okay, good afternoon. Let's start the lecture. And the main topic of today will be static failure of brittle material. Okay, but I'm gonna go over an example on static failure of a ductile material first. Okay, and then we'll touch on the new concept, the static failure of brittle material. So just a quick review, and this is a part of the this is the picture in the handout. So if you don't have it, you still get some here. We covered two different theories in terms of the static failure for ductile material. One is the maximum shear stress theory. The other is the distortion energy theory, right? The graphic here is the basically the graphical locus for the two theories. Okay, within this curve or the boundary, it's safe. Outside it, it's not safe, right? The solid one is the distortion energy theory, the ellipse, and the hexagon is the maximum shear stress theory. Okay. So take a look at the handouts and see if you can get all the information right. Now, in short, okay, when you use maximum shear stress theory, basically what you're comparing or how you determine if you have a safe or a failure or not, you're basically comparing the maximum shear stress, okay, with the shear strength. The way to calculate the tau max is always based on the principal normal stress in 3D space. So sigma 1 minus 3 over 2. Okay, and that's the shear strength used by Mss theory. And when it comes to distortion energy theory, if you recall that in previous lecture, is basically the reason is because people find the failure mostly because of the distortion strain energy. So after certain derivations, we derive at an equation. What we compare is we compare the von Mises stress sigma prime versus the SYT. So von Mises stress, there are three different basically equations I given to you in the last lecture. One of the equations is a general one here. I didn't have it here. That equation is based on the three principal normal stresses. But usually what we deal with the plane stress. So these two equations here are von Mises stress, how you calculate based on the plane stress. Okay. So for example, if you know your principal normal stress for the plane case A and B, then this is the equation. If you have the state of stress for the plane stress, and you can use this equation, right? Okay. So either way is fine. Okay. But however, you should know that in distortion energy theory, the shear strength is 0.577 SYT, so it's slightly bigger than the shear strength used in Mss theory, right? So that basically tells us the Mss theory is a little bit more conservative than the DE theory, which can also be explained by the graphic here. As you can see, Mss theory is inscribed within this DE theory. So when you have a point here, it's considered safe according to DE, but it's not safe according to the Mss theory, right? Yeah, so that's the basically in the short, that's what the DE and MS for ductile material. Okay. So let's take a look at the example. Okay. So for this example here, so what we're going to deal with is a situation like this. So let's say I have a bar. Okay. So that's a bar fixed on the wall on this side here, and then you have a handle over here, with a force applied down over here. Okay, so that's the loading for this bar here. So this side here is affixed to the wall. Okay, it's fixed to the wall, and there are some dimensions on this bar. For example, we know that the length is A, and the length over here is L. Okay. And this side here is a handle. This side here is a circular bar here. So this side is circular bar. Okay. And the circular bar has a diameter D. Okay. So that's roughly the dimensions we need to know at here. All right. So the L is 6 inch, and A is 8 inch, and the diameter D is 1.5 inch. Yeah. The F is 1,000 pounds or 1 kip. Okay, doesn't matter. Okay, so that's the loading condition now. Now let's take a look at what we need to do. We want to analyze so we want to analyze the safety factor of this rod at the end over here. Okay, so we want to see basically, are we going to have a failure or not failure situations for this rod here. So we're going to look at the location over here, because the reason is this is going to be the critical location at here. Okay, yeah, so we can see that. So we're going to analyze the end of the rod, over here. So to analyze the end of the rod, so generally what we are interested in the critical location, basically. So if you look at the rod, the end of the rod here, it's a circular cross section here, right? Circular cross section. Then there are infinite number of points on the circular cross section. So the key point here is, which point shall we look? Where is the critical location, right? Yeah. Okay, before you do everything, what you do is generally for any mechanical system, and you need to draw the free body diagram first, to indicate or to calculate some of the unknown forces. So if I draw this free body diagram in here, so let me just kind of redraw this thing in here. So this is basically the system, right? This is the system, and on this side of the system, you have a force going down at here. You have force going down, and the system is under equilibrium. It's in equilibrium. When the system is in equilibrium, that means what? That means, as you can see, this is the body you're analyzing. That means there's some action-reaction forces or moment from the wall, right, to balance the system. So very simply to put it, from the wall, that the force to balance this one has to go what? Has to go up, right? Has to go up. So this force will balance this. At the same time, you look at this force that is here, it's going to generate two moments. So if, for example, if I draw a radius right from here to here, so use your right hand rule. Moment is r cross f, right? Moment is r cross f. So from here to here, so this force F is going to generate a moment in this direction and here. That makes sense, right? The right hand rule. So always remember, how moment is r cross f, right? It's r cross f. Yeah. So for example, when you draw the moment, you draw it from here to here, that's r, then this r cross f, that's the moment, right? Basically this f will generate a moment, right? According to the right hand rule this way here, basically it's gonna create a moment in this way here, right? In this way. But we don't call this moment, because you see this one here, this guy, or this moment, it's concentric with what? With this axis of this cylinder here, right? So what we call this is a torque. So we can call this a torque here. So the F will generate a torque in this direction, right, along this rod here. Then in other words, the wall has to generate a torque to resist that torque, right? To resist that torque. So if I draw the reaction moment or reaction torque from the wall, instead of drawing this direction, then you draw that torque in which direction now? In this direction, right, from the wall. Is that clear? Yeah. So that's the first moment, or what we call the torque, generated by the F, and the reaction one from the wall to keep the system in equilibrium. Yeah. Now this is one direction, right? This is one direction you draw this distance. Now if you draw the distance from this location up to here, up to here. So basically the force has a shorter distance from here to where? To this. This is a shorter distance, L here, right? This is a shorter distance. So as you can see, another right-hand rule from R cross F. So F generates another moment, right? The F generates another moment about this point at here. R cross F. Now this time, if I draw it, right? If I draw it, this R cross F, what direction is that? It's this direction here, right? This bending. Basically, this is a bending. This is a moment that we're talking about here. Okay, so we call this moment instead of calling it torque. Okay? So basically, this F will generate a moment about this point in this direction, and the wall has to react or to counteract this moment here. So which means, so I'm going to erase this one here. Which means what? Which means from the wall you have, so I'm gonna, let's extend this axis at here. From the wall you have a reaction moment to counteract this moment generated by at here, R cross F. So that direction will be this way, right? Will be this way. Now, the drawing is a little bit, you got to be careful here. This T, this T is in basically around that axis here, right? And this M at here is actually about which one? This M here is actually about this axis here. This axis. Take a second look at this one, see if you can get through this part, because this is actually critical. A lot of the time when you're gearing system, you have to successfully draw the free body diagram first. Can you see where the M from? That this M is trying to counteract the moment generated from here. You see this F multiplied by the L, that's a moment, right? That's a moment. And that's how much is it? And what direction is that? That's the direction here. And then from the wall, you have the counteract direction here. Did I draw it right? Yeah. Right? Yeah. So basically, from the wall, you have this moment, and that moment, if I draw it over here, that moment is gonna be, let me see, that moment's going to be maybe, which way is that? That way, right? The other way. It's this way here. It's going to be around this axis here. Going to be around this axis. Is that clear? Yeah. So maybe I'll get rid of this one at here and put this M over here. Yeah. So that's the free body diagram. So the whole system is in equilibrium, and you need 1, 2, 3 from the wall to balance the single force over here. Single force over here. Is that good? Yeah. So now the question is, what are the values of each one of them, right? So this is actually quite easy to calculate. This is F, basically the same as that, and the T is the one that's trying to balance this F multiplied by this distance. So that's F multiplied by A. And the M is F multiplied by L. So F by A, according to this 1,000 by A, so 8,000. So pound inch. F by L, it's 6,000 pound inch. Yeah, that's the two: action, reaction, torque, and a moment. Yeah. So once you get this ready, so then what we're going to do is, remember where you're analyzing. You're analyzing the location at the wall here, right? A location at the wall. So what we do is we cut a cross section. Basically cut a cross section right in front, or right in front of the wall here, as close as possible. Okay, so cut a cross section through the rod as close as possible to the wall, right? Yeah. So maybe I'll put down my coordinate system first. Okay, so we need that to be more precise. Let's say this is my y, this is my x. Okay, this is a z here. So x, y, z, satisfying the right-hand rule. Okay. Okay, so we're gonna cut, okay, a cross section. Okay, cut a cross section, okay, in front of the wall. Okay, and I'm gonna basically, now when you cut a cross section in front of the wall, and in other words, actually, I have a different ways of looking at the cross section. So I'm going to look at the cross section from the positive axis point of view here. Okay, so this is my positive axis, right? So this is what I said. I'm going to look at, okay, from the positive axis, okay, direction. Okay, I'm going to look at the cross section from this direction here. So what that means is, when you cut a cross section in here, so what you have here, you have a circle, right? You have a circle, okay? And where we're looking at, the direction we're looking at is the positive x-axis. So then this is y, and this is your z, right? So it's like the front view, okay? It's a front view here. So this is my cross section here, okay? And essentially, it's like you can imagine, right? You can imagine as you have a very, very thin slice, okay, right in front of the wall, and this is the front view of the slice, right? And there's a very small thickness, then the other side it's attached to the wall. That makes sense? Okay. So now for this cross section here, then based on our free body diagram, let's put down, okay, let's put down the loading condition on this cross section here. Right? Yeah. So you see, on the other side, remember, the other side of the cross section is the side on the wall, right? Which means on the other side, it's basically, what's the loading condition? FTM. Okay. So then on this side here, you have a totally different direction, this, to counteract the other side in order to maintain that cross section to be in balance. That makes sense, right? So in other words, based on this cross section here, what loading condition do we have? We have a shear force. This shear force, in order to balance the other side, it should go up or go down. This cross section is right in front of the wall here. So it's like you have a slight small thickness over here, right? Small thickness of a slice set here. So this side is the wall. What do we have from that side? It was F, T, and M, right? From the side of the wall. So on this cross section, which is this, you need to have the same thing. You need to have the three things to balance these things here, right? To balance this. So the shear force on the cross section, if this is going up, then this side here is going to what? Yeah. Okay. And you also have a torque on this section here. Since that side goes that way, so this side should go which way? This way, right? Yeah, counterclockwise. Okay, so this is a T, and there's a V equal to F over here. So that's what you see here, right? And at the same time, right? At the same time, you also have this. The other side of bending moment in this direction. Then this side of bending moment, right, should be this direction here, right? Should be this direction. Okay, so that's, I can't draw it over here, but I can draw it here. So that's basically the three things that you see, that when you look at it from the positive x-axis direction, that's what you see, the three things on the cross section. Okay, that's what you see. Why this is important? Because when you analyze this critical moment, or when you analyze this critical location, you need to know what the stress, right? What stresses there is on the cross section. Okay, yeah. Okay, so now we're ready to analyze this cross section now. Okay, so the way to analyze cross section is remember some of the particular or special values. Okay, remember for bending moment, right? For bending moment, what's the special characteristics bending moment? It causes normal stress, bending normal stress, right? And it causes always a maximum at top and bottom, right? So basically, the one is in this is a tension, this is a compression, and on the neutral axis, in this case the z-axis, the bending normal stress caused by the M is always what? On the neutral axis, 0, right? It's 0. So essentially means at this location there is a critical points over here. Okay, and this shear force, okay, this V at here, this V will give you a shear stress, and a shear stress is always maximum at this neutral axis location here, but 0 at the top and the bottom. So in other words, this location here will be a critical location. So what we're really interested, we're really going to look at is just this location and this location. Okay, yeah, because both of these locations give us a maximum, right, due to the loading condition. Okay, but which one is more critical? That we have to make a conclusion after the calculation. All right, yeah. Was that good? Okay, so now let's take a look at I guess I call this is A, this is B. Let's take a look at the A first. This is A here. Okay, let's look at this A first and then look at the B here. Okay, so look at the location A. Okay, let's look at the location A. So when we look at the location A, and essentially what we do is we're going to draw a stress element, okay, out of the location A here. Okay, yeah. Okay, so here's a cross section. I'm gonna draw a stress element out of the location here. Okay, out of the location A. So this is the front. This is basically a small rectangle here. So then what you do is you extend that rectangle. Okay, that's the stress element we're gonna draw. Okay, yeah. So for this stress element at here, so I'm gonna basically take out the stress elements here. Okay. So take out the stress element, and that's the front view here. Okay, that's the front view. So let's say what kind of stress are on the surfaces of this stress element. Okay, and that based on purely based on the loading condition, right? So let's take a look at what stresses do we have on this elements here. So let's see, look at this surface here. What stresses do we have? Here is MFT, right? MFT. Does V or does F cause any stress at this location? No, right? Okay, how about this T? This is a torsion. So the T, does T cause any stress? Or if it causes any stress, what do we call that? Shear stress. Yeah, so T will cause a shear stress. And what direction is the shear stress? This way or that way? Here's the direction of the T. So the T acts on the surface, right? It goes this way. So that shear stress must go this way too, right? Let's go this way. Okay. So that's one stress. That's what we call the tau, right? That's the T. The torsion gave us a tau, and the value is always TR over J. Okay, TR over J. Okay, yeah. And the M will also cause a stress. That's bending moment. So this M will cause a so-called what? Bending normal stress. Yeah. And the direction, because this is the equation we're looking at, so it's tension. So what you do is you draw, right? You draw it out of it, right? So let's call it sigma here. Okay, call it sigma. Okay, Yeah. So what's the value of sigma? It's m r over, not j, m r over I here, right? M r over I. So those are the values, right? This is the value here. Now, to be more precise, okay, I'm going to draw this stress element in the x, y, z coordinates that we designated in this question here. Okay, yeah. But however, let's finish this stress element first. So on this cross section, on the section here, here is the two stresses, right? And there's nothing else. Okay. Now, how about this surface here? Is there anything here? Remember, this is a stress element imbalance here, okay? Imbalance. So for this side here, do we have anything? Or maybe let's try this side here. Over this side here, do we have anything here? Balance, right? Remember, it has to be balanced. If this has to be balanced, this side has to have something here, right? Otherwise, it's not balanced. So you're going to have two stresses on this side here. One must be what? That's right, right? So this has to be the same magnitude as this guy here. Are you going to have one of this one here? No, right? No. Okay. So how about on the opposite of this over there? So what are you going to have? You're going to have what? A sigma, right? Imbalance of this guy here, right? Imbalance of this. Okay. Yeah. Okay. So there's not going to be anything on the top. Okay, right? There's not going to be anything on the top. So that's basically the stress element. This is what we call what? Remember, this kind of thing is what we call a plane stress, right? Plane stress. Because when you look from the top, right? When you look from the top, all you see is basically it's something like this, right? It's something like this. That's what we call plane stress. There's nothing on this surface here. Okay? Yeah. Okay, so to be more precise, I said I'm going to put this thing here in the XYZ coordinate system that we have here, right? So what's my XY coordinate system? This is Y, this is Z, and this is X here, right? This is X. Now take a look at where this is from. This is from this location here, right? This location here. So where's X? X is this way, right? X is this way. And where's Y? This is Y, and this is Z here, right? This is Z. So if I put this stress element in this XYZ coordinate system, so in general, usually what you draw is you draw the XYZ coordinate system like this, right? Like this. Okay? Yeah. That makes sense, right? So just a second here. Let me draw it because the orientation here. Let me draw it. Let me draw it slightly different here. Okay? So this is my Z. This is my X. This is my Y at here. Okay? So basically, the coordinate system is we're gonna look at this, slightly rotate this coordinate system a little bit here. Okay, slightly rotate it to here. Okay, so if I do this, and when you're rotating this rotating system, these elements will also be rotated slightly, and if I draw that same stress elements at here, okay, draw it same at here. So guess what? This side is actually which one? It's this side here, right? It's this side. Okay? Yeah. So basically, I have a sigma. This sigma is this guy here because it's pointing in the positive x direction. So we're going to call it sigma x at here. Okay? So that value is mr over I. Okay? Mr over I. And this tau, okay? In this case, it's pointing this way here, right? Pointing this way. So basically, if I draw it here, where is it pointing to? It's going to be pointing this way here, right? Pointing this way. Okay. So that tau is tr over g. So more precisely, the subscript at here, instead of calling it a tau, because this is in the which plane? The xz plane. So the subscript at here, more precisely, it should be tau xz. Okay, tau xz. Was that good? Yeah, there's a lot of little details at here, okay? But you can relax actually in the future. I'm not going to be too picky about the details. At this stage, I'll be, because we just started, so let me do it right for every details here, okay? In the future, okay, more often is, what you're interested is just the absolute value. So even if you messed up with the subscript, this guy here or this one here, that's fine. right? All that matters in the end is what will be the maximum stress at that location. Okay? Yeah. But at this stage, let's get to the detailed side. Is that good? So on this side here, you have one thing to balance that, right? One thing to balance that, tau xz to balance that. Okay? And on this side here, you have a sigma, also sigma x, right, to balance that one. Okay? So that's the stress element taking out of the location A. Taking out of location A. So if I do the calculation of these two first, so let's do the calculation of these two. And that's pretty easy. So sigma x is m multiplied by the radius. And the radius is half of the diameter. And I is the second moment of the area. Okay, so basically the cross section is a circular. If you remember, the formula is pi d to the power of 4 over 64. Okay, yeah, so that's I value. So you have everything out here. D you have, m you calculated, so this can be calculated easily. Okay, yeah. So in both of our exams, so you need probably a good engineering calculator to help you deal with calculations. All right. So I'm gonna skip some of the calculation here. Just put down the numbers. So we get this number stress. Okay. So that's sigma x. And the tau x at tau xz, it's tr. Again, the r is half the radius, and j is the polar moment of inertia, and for cross section the circular, it's 32. Okay, 32. Okay. So remember these formulas. Okay. Yeah. So save you some times. Is everybody following here? Is okay? Yeah? Good. So calculate this. That's 12072 psi. Okay? That's it. That's the two stresses, okay, that we can easily calculate. Okay. Then the question is, we are not just looking at the state of stress taking out of the location A. So what we're looking for is the maximum stress, right? The maximum value. Okay, but at this location here, at this location, all right? Yeah. So in general, what we can do is we can calculate that two principal normal stress, okay, based on the state of stress at here, and the formula, right, that you should be able to memorize now. If not, that's okay. Okay, so this is the formula, right? This is the formula for the two principal normal stress. Okay, but there's a little confusion here. The general one is sigma x, sigma y. You gotta basically a little bit careful here. So this is a sigma x, sigma y, and then tau xy, right? That's the formula for this one here. Okay, that's the formula for this. Okay, so in our case, so if you look at this, our state of stress here, this is our state of stress. If you're looking from the top here, right? If you're looking at the top, so basically what happens is it's a slightly different from this one here. So let's see, if I'm looking from the top here, what do I see? So looking from the top here, what do I see here? So looking from the top, this is x, this is z, right? This is x, this is z. And I have this one here, I call this the sigma x. And we have, sorry, that way. We have these two here, we call that tau xz, right? Call it tau xz. Make sense? Oh, sorry, yes, positive z, that's right, yeah. Positive z, that's right. So this goes this way, that goes up, right? Yeah. Okay. So, in other words, when you plug this one here, right? When you plug this one here, it's probably a little bit confusing as to which one that you should plug it here, right? So, in other words, if you really want to be accurate to every direction, so this sigma x is, in this case, is actually what? 0. So that sigma y over here is this x here. Is that right? Yeah. And this tau xz is the tau xy over here. But it really doesn't matter because there's a square here, so the arrow may be different from the general status, but it'll be canceled out when you take a square here. Is that right? Yeah. So basically, when you plug in the state of stress into the general formula, right? And to be more precise, you want to basically have a one-to-one comparison at here, right? Yeah. Okay. So, in other words, if I plug it in, so what am I gonna get is sigma AB in my case. So what do we have here? We have basically sigma x over 2, because one of them is 0, so divided by 2 at here, plus minus a root, right? And sigma x over 2 square plus 3 tau xy square at here, right? Here. Does that make sense? Yeah. So you might think, oh my God, am I gonna make a mistake if I don't get this thing right, right? But don't panic. As I said, even if you don't get all the one-to-one comparison right, but if you know this formula, look at what happens, right? Let's say even if you draw this is wrong, if you draw the sigma x over here, but when you plug it into this formula here, you're actually not going to make a mistake in terms of the calculation. Okay? See, doesn't matter which one is 0, I always have a sigma x or sigma y here, right? Yeah. And when you plug this one here, the square root, there's a square here, so negative is always gone. Okay? Yeah, same thing, the negative is always gone. So the value of the calculation, it's not gonna mess you up. Okay, even if you don't draw this right. All right? Yeah. So don't panic about this thing here. But of course, at this stage, if you want to get everything right, okay. So this is what you should do. Okay. So you plug in the numbers, okay, into the formula right here. Okay. So what we're gonna get, we get 24144 and 036. Okay, we get these two numbers. Yeah.
Is it meant to be 3 tau xy or just tau xy?
Tau xy. That's right. Sorry. Yes. Good point. Good point. I was thinking of that one misstressed formula now. Yeah. Thank you, Josh. Yes. Yeah, if you got that wrong, definitely the calculation will be wrong. So, you look at the two values at here. Sigma A is greater than 0 and greater than sigma B, right? Sigma B is less than 0, okay? Less than 0. So basically, if I want to apply the failure theories, right? The number one, let's try that maximum shear stress theory. So for maximum shear stress theory, what do we compare? We compare the maximum shear stress with what? With the shear strength, right? With the shear strength. So we compare this with that. So the question is, what's the sigma 1 here? What's sigma 3 at here? So you look at this one here. How do I know what's sigma 1, what's sigma 3? Sigma 1 is what? Sigma 3 is what? So if you're not too sure, take a look at the handouts that you have there. Take a look at the second page. there's a table. Over here, this table here. Those are cases here, right? So those are how you determine the sigma 1, sigma 3. So tell me which case we're dealing with. Case 2. So basically, this is how you're going to calculate the safety factor here, right? It's going to have a safety factor. Okay? So then according to the MSS, okay, according to MSS, the safety factor N is going to be SYT according to this formula, right? It's this guy divided by this one here. Okay? Yeah. So if you want to write everything, this top one is, let me write down. It's SSY at here and tau max, right? Tau max. Okay. And SSY is half SYT. And tau max in this case is sigma A minus B over 2. So that's why you see in that folder, in that table, it's SYT over sigma A minus sigma B, right? Yeah. Okay. So you have a sigma 1, which is sigma A. You have sigma 3, which is sigma B. You have SYT. Oh, I don't have SYT yet. What's the SYT? SYT is 47,000 psi. So SYT is 47,000 psi. Okay, so that's aluminum kind of material. Okay, it's ductile. Okay, so plug in everything here. Okay, and do the calculation, and that's approximately 1.6. Okay, it's approximately 1.6. Was that good? Right. So then, according to the DE theory, then the way to calculate the N is SY over sigma prime, right? Sigma prime. So what we need to do, we need to calculate the sigma prime first. And sigma prime is the von Mises stress. Now there are two formulas, right? So either this or that. Okay, so it doesn't matter. So what we already have is what we already have here. So what do we already have? We have sigma x tau x z. So in other words, if I go back to this equation here, so in other words, what we have here, I may not know what exactly which one is sigma x, sigma y here, but I do know is one of them is sigma x or sigma y, and the other one is going to be 0, right? Going to be 0. So it really doesn't matter. So let's say I assume that's sigma x, this is 0. So just sigma x squared plus the 3 tau x z squared, right? That's what we really need to know. Okay. Yeah, the 3 shows up here. So do a simple calculation, and we can get 27,661 psi. Okay, yeah, psi. Then the safety factor is this 47,000 over the sigma prime, and that should be approximately 1.7. 1.7. Okay. So does that make sense? Let's say if you do a calculation for the same spot, okay, for the same spot, you calculate your DE, which turned out to be 1.5. I think you should stop there and take a second look at your calculation. Why is that? Exactly, right? Exactly. Because the MSS is more conservative than DE, right? If your calculation is a little bit lower than that, then there has to be something wrong somewhere. Okay? Yeah. So that's location A, right? That's location A. So now let's look at location B. So I think once you know the location, how to calculate location B, so the way to handle it, it's very similar. Okay, very similar. Okay. However, it turned out the location B has an absolutely different state of stress than location A. Okay. Yeah. So this is the location B we're looking at here. if I do the same thing, I'm gonna draw a stress element, okay, at that location here, okay. So basically, if I blow it up, I have a stress element, okay. Front side is here, okay, and that's the other end. Okay. So, what are the stress distribution on each side of the cube, right? That depends on the loading condition. So what do we have at this cross section? We have a torque, we have a shear force, we also have a bending moment. Okay, as we said, bending moment causes a normal stress, bending normal stress 0 at the cross section, at the neutral axis, which is the B location. So that M not gonna give us any bending normal stress. Okay, so which means at the B location you're not gonna get any normal stress out of that cross section. This V will give us a shear stress, and it's actually going to be a maximum because this is the neutral axis location. And the torque T will also give us a torsional stress, right? Torsional stress. And the direction, right? The direction caused by the V, it's going down because the V at the cross section going down. And direction of the torsional shear stress caused by the T also goes down, right? They go to the same direction. So the formula for the torsional shear stress is the same as previous location A. The formula for the shear force, the shear stress caused by the shear force, is going to be, there's a formula, right? There's a formula. So the formula is basically, this is a circular cross section. This circular cross section, and that formula is 4/3 V over A. Okay, 4/3 V over A. This is circular cross section. So if it's a rectangular cross section, is 3/2 V over A. Right? Yeah. So those are all given in the review in our first week of lecture. Okay. So you got two stresses going down, okay, by this direction. So then the total, let's say call it total, is basically this plus this. Okay, it's this plus this, right? Okay, so this is basically all the stresses that we have, right, on the cross section. And if you draw it everything out, basically to balance that, you have two things here on this side balanced. There's nothing in here, right? Nothing here, and only stresses around this direction here, right? Around this direction. Then it has to be balanced. Okay? Yeah. Now, if you wanted to do, okay, precisely as what we have done for the location A, then you have to look at this coordinate system and label this properly, right? And look at that stress element, okay, properly in the coordinate system given. Otherwise, okay, remember what we need. We actually only need what? We actually only need the absolute value, right? So based on this, the drawing that we have here, you know what do we have? We basically have a plane stress. Right? We basically have plane state of stress, and plane state of stress, all we have is a tau total. Did I draw this right? I'm not sure, right? That's basically based on the coordinate system that you have, but that's what we have here, right? That's what we have, and if this is what we have, then I need this absolute value. What absolute value do we need? According to the Mss theory, I need what? I need the tau max, right? And according to the D theory, I need the sigma prime. That's all I need, right? All I need. So based on the information right here, my tau max is actually, this is a pure torsion, right? This is a pure torsion here. So basically the tau max is this tau total at here, right? It's this tau total. Okay? That makes sense? Yeah. And then I can do my Mss theory now, right? Mss theory. So let's see, I haven't calculated this yet. So if we do the calculation of this one here, you're gonna get 12072. Okay, you're gonna get this. Okay, you're gonna get this. So then according to the MSS, so what we need is, we need safety factor, which is 1/2 SYT over tau max. Okay, 1/2 SYT over tau max. Okay, so 1/2 47,000 over the 12,072, approximately 1.8. Okay, 1.8. Okay, yeah. So that's the safety factor based on the maximum shear stress theory at location B. Right? So apparently, location B has a slightly higher safety factor than location A, right? And location A. So in other words, which location is more critical? Location A. Yeah. Okay. Yeah. So if I calculate the DE, I need the sigma prime, right? I need sigma prime. Sigma prime, based on this state of stress, there's no sigma x, there's no sigma y, and all you have is a tau. So basically it's what? √3, this tau total, right? Tau total here. Okay? Yeah. So that's your sigma prime. Okay, sigma prime. Okay. Then the safety factor, okay, is SY over √3 tau total. Okay, tau total. Okay. Okay. Let's observe a very interesting thing here. Okay, very interesting here. Look at this one here. Okay, look at this one. If I write it slightly different, okay, it's SYT over √3 over this tau total. All right. Yeah. So what's the top here? What's the top? Remember what do we call this one here? SSY, right? That's the shear strength according to the DE theory. So this is your SSY according to the DE. So what are we comparing here? We're comparing that with the shear stress in the element at the location, right? Element location. You see, this is exactly the same thing. What happens? This is the pure shear. So that now you have a one-to-one comparisons when the DE with MSS here. Okay. So apparently this is going to be higher. This is approximately 2.1. Okay, 2.1. Okay. Okay. So this is basically a typical example. Okay, this is actually, I would say, a little bit challenging ones. Okay, because it has a combination of different loadings. Okay. But however, okay, when you do this at the early stage, I want you to try to do everything right. But you also need to realize is, in the end, when it comes to design, and really all you need is what's the maximum value, what's the critical location we are looking at, right? Yeah. You don't have to draw every element right, but you need to calculate the absolute value right. Okay, that's really what happens in the end. All right. Now the other observation out here is this. Okay, the other observation. Now you see, we have a cross section, and we're looking at A and a B, and we understand that at A here, it has a zero shear stress due to the V maximum bending normal because the M. But the B here has a zero bending normal because the M, but it has a maximum shear stress due to the V, right? Okay. So now the natural question you're probably going to ask is, okay, if I have a shaft and I'm going to design for this shaft, so am I going to look at every time? Am I going to look at always have to find the A and the B and then see which one is critical or not, right? So that's one of the things that you should actually maybe ask yourself now. The answer is you don't have to. Okay, most of the time, the bending normal stress caused by the M has a stronger effect on the cross-section than the shear stress caused by the V. Okay, so as actually, if you look at this, the A and B, what's the difference between A and B? They all feel this shear stress, torsional shear stress, right? They just don't feel, one feels the M, but the other feels the V. So according to experience, the bending normal stress caused by the M generally has a more critical effect on the cross section than the V at this location. Okay, yeah. So remember that. Remember this what I just said here. When you design for shaft, okay, most of the time what you do is you can neglect, if you have this loading condition exactly like this one here, right? You can neglect analyzing location B. Okay, yeah. But that's just sort of a rule of thumb here, not always true though. Okay, yeah. Okay, is that clear? No good? Okay. So that should put a dot on the ductile material for the static loading for ductile material. So then let's look at static loading for brittle material. Okay. Okay, so for brittle material, what we're going to do is we're going to look at 3 different theories. Okay, so one of them is called maximum normal stress theory. The other one is called what was it called again? Brittle Coulomb. So Brittle Coulomb Mohr theory. So BCM theory. So Mss BCM, and the last one is modified Mohr. So MM. Okay. Yeah. Not the chocolate, but okay. So now 3. Okay, so that's the 3 theorems we're going to look at it here. Okay, and they are very closely connected to each other. Okay, but first of all, let's establish a certain fact. Actually, I think I mentioned this in the previous lectures. So for brittle material, according to experiment, it generally fails due to what kind of stress? Pardon me? What kind of stress? Ductile material, we said, generally fail due to what? Shear stress, right? So the brittle material generally fail due to normal stress. Okay, so this is actually you can see now. Oh, normal stress. That must be where this first theory name comes from, right? Yeah. So this is what happened for the first theory right here. So what we do is we basically. So here's the first one, Mss theory. So according to that experiment thing here, this is the definition, right? Definition. Okay. So Mss theory says failure, when one of the principal normal stress exceeds the strength. Okay, that's basically what Mss theory says. So one of the principal normal stresses, and we're looking at the 3D, right? We're looking at a 3D. So basically what happens is we have sigma 1, sigma 2, sigma 3. And that the question basically saying is one of them is greater than the strength, then you have the failure, right? You have the failure, okay? And actually, it's not going to be sigma 2 because sigma 2 is in the middle, right? So it's not going to be the term of sigma 2. So the strength that here, if you remember for brittle material, we actually have two different strengths. One is SUT, the other is SUC, right? Yeah. So one is the ultimate tensile, the other is ultimate compressive, and these two are generally not the same, and that's actually what we still call the uneven material. Okay, uneven material. Yeah. Now there are situations they are close to each other, but we're dealing with mostly uneven material. For example, gray cast iron, right? Yeah. So in other words, according to the definition here, when one of them exceeds this, and the other fact you should know that is SUT is slightly, not slightly, okay? It's actually sometimes much less than SUC, okay? Yeah, gray cast iron, SUC about 3 or 4 times bigger than SUT, okay? Ceramic material will be even having higher ratios. So basically, then what happens is which will be possibly exceeds SUT? The only possible one is when, right, sigma 1 is greater than SUT, right? SUT. And the other possibility is when sigma 3 is what? Is less than, now sigma 3 is possibly negative value, but you're comparing with a positive value, so when you can put a negative sign there, right? Negative sign here. Okay? Yeah. So that's basically what Mss theory been telling us here. So what do we compare? We look at the 3 principal normal stress. If this is greater than that, it's a failure. If this is less than that, it's a failure. Okay? Yeah. So I guess it's best that I will illustrate this using Mohs circles at here. Okay? Mohs circles. So it's actually quite simple. So when I use the Mohs circle, if this is tau and this is sigma here, okay, we have 2 critical values. One is SUT, and the other is negative SUC. Okay, negative SUC. Okay, yeah. So if I have a Mohs circle, and when we draw the Mohs circle, if you recall that this is always our premises. We deal with the plane stress, but we look at it in a 3D case, right? 3D case. So the first case, maybe my Mohs circle is over here. Okay, that makes sense, right? Maybe my Mohs circle is here, and this is sigma A, and this is sigma B, right? It could be my first case here. Okay, yeah. So in other words, this is the case when you have. This is the case. Alright, let's see number 1 case. This is the case when sigma A greater than sigma B greater than 0. Okay, greater than 0. So when you have this case right here, according to the Mss theory, right? Is it possible to? Okay. When you have this case right here, what is the sigma 3? Sigma 3 is 0, right? It's 0. Is it possible to have this one here? Not at all, right? With sigma 3 is 0, how could 0 be less than this guy here, right? Less than this guy, meaning the value has to be somewhere here, right? Yeah. So it's not possible. So when you under this case here, the only possibility is this one here, right? And the possibility for this one, because sigma 1 in here is sigma A, right? Yeah, sigma A here. So in other words, according to this case right here, then your safety factor is actually always what? The ratio between these two. And the sigma 1 is sigma A, right? If sigma A is greater than SUT, in other words, the circle, this side move up beyond here, you have a failure, according to Mss. That makes sense? Yeah. Yeah. So not that hard to understand here, right? Okay? Yeah. Now, second case is when sigma A is greater than 0, greater than sigma B. So let's say if I monitor this case right here, according to the drawing, let's say I have SUT, SUC. So when you have this kind of state of stress, the Mohs circle must be what? Must be something like this, right? Must be something like this. Okay? Yeah. And here's A, here is B. Okay, here's B. Okay, here's B. Okay, so when you have this case set here, so what is sigma 1? That's sigma 1. What's the sigma 3? And this is sigma 3, right? This is sigma 3. Okay. So you look at the way I draw the Mohr circle. Is it possible? So what the way I draw the Mohr circle is maybe what? Maybe the circle could be like this, right? Is that possible? Right? Yeah. So basically, when I draw the circle like this, in this particular case, then sigma A is greater than SUT, and sigma B is less than negative SUC. Right? But according to the Mss here, failure occurs either this or that, right? Either this or that. So basically, under this case, that either or could happen at the same time. That right? So basically, you could have sigma A greater than SUT, and the sigma B less than SUC, right? Occur at the same time. Right? It could. Right? It could. Okay? Yeah.
In that case, the circle is centered at 0, right?
No, not necessary.
Okay.
Yeah. Because sigma A, center at 0 meaning sigma A, sigma B are in the opposite of each other, right? Yeah, not necessary. Yeah. Okay? That make sense? Okay. So then the natural question is, if I wanted to calculate the safety factor, right? Safety factor in this case, then what we're going to have to do is we have to check these two conditions at the same time. We have to check both conditions, right? So in other words, we have to check what is the value of this. Okay? We also have to check what is the value of this. Okay? You have to check both conditions. And let's say this value give you is 1.1, and this value is 0.9. So what would be your conclusion? You would take this 0.9, right? And your conclusion will be failure. Is that right? So if I mathematically want to express what we just said here, we wanted to take the mean value out of this guy here. Take that as the safety factor. Okay, right? Take that as safety factor. Okay. So that's the second case. All right. This is the second case. Was that good? Yeah. Okay. So the third case is when 0 greater than A greater than B. Okay. That's the third case. So if this is the case here, do the same thing. I think you can find that easily based on the previous two cases. So the circle, the Mohr circle, will be within here now, right? Will be within here, and that's A, and that's B. Okay, that's A and B. Because both are less than 0, so they're not going to go to the other side here. They're all going to be here on this left side of the axis. Okay, left side is the y-axis. So if this is the case here, is it possible for sigma A to be greater than SUT? No, right? So the only possibility is to compare the sigma B and the negative SUC. So then your N is just basically, okay, just basically this. Okay. So that's Mss theory. Okay, that's Mss theory. And if I draw the root, not the root locus, if I draw the safety locus, okay, for this Mss theory, so then what we need is we basically very similar ways drawing, okay, like the previous one here. You look at this. This is what's the first case? The first case is sigma A greater than sigma A greater than 0, right? Yeah. So that's basically somewhere here. And what we're comparing? We're comparing SUT with sigma A. Okay, sigma A. That's right. This is A. This is B. Okay. That's the first case. And the second case. So what you're doing is you're comparing this, and take the mean value. So actually what happens is, what you have here is basically you have a boundary like this at here, okay, boundary like this, okay, and the last side of boundary, it's over here, okay, it's over here, the case number 3. So if we finish this this locus, okay, we get basically a rectangle. Yeah, my drawing is not that accurate, but it's not a square, no? It's basically a rectangle here, okay, rectangle. Is that good? Yeah, that's the simplest theory. Basically, it's always compared with the maximum normal stress that is here, okay, maximum normal stress. Any questions? Yeah, all good? Okay, so let's continue on the next one here, and then I think we can finish the next one, the BCM theory. Maybe not, but let's start BCM. Okay, the BCM, the Brittle Coulomb-Mohr theory. Okay, the Brittle Coulomb-Mohr theory. Now, before we start BCM, let's come back to this case at here. Okay, come back to this case. Okay. So in this particular case is when sigma A greater than 0, greater than sigma B, and this is one type of a Mohr circle. And what you could also draw is what? You could also draw this Mohr circle, right? You could also draw what? A Mohr circle like this, right? A Mohr circle like this. But as long as the two ends of the circle are still between this SUT and the negative SUC, you're safe, right? You're safe according to Mss. But you can imagine, right? You can imagine. You can have a pretty big circle, right? A big circle. Then the problem with the big circle is what? You will have a pretty big what? Shear stress. Exactly, right? Your maximum shear stress will get ridiculously big. But according to the Mss, you're still safe, right? Yeah. So that's the problem with this region right here, okay? This region. And experiment also shows that even if Mss is safe, but it's already filled. Okay, it's already filled. And what's the reason? That's just because the reason is the Mss theory at this quadrant, okay, at this case, it didn't consider the effect of the shear stress, right? So that's basically where the BCM come into the picture. Okay, BCM. Okay, so the BCM, there is a history at here. BCM, we talk about Brittle Coulomb-Mohr, and this Mohr theory basically is the foundation here. Okay, this Mohr theory. Okay, so the Mohr guy says, okay, and in the past he was trying to develop a failure theory, right? So he comes up with a pretty neat idea. Is this? So he was saying is, okay, so I'm gonna you give me material and you ask what under what conditions it's gonna feel, right? So let's do 3 different tests on the material. One test is the tensile test. Okay, one is the tensile test. So if you do a tensile test, you get a Mohr circle like this, right? The other test is a torsional test. So basically testing the shear stress. When you do a torsional test, you get a Mohr circle basically like this, right? Like this. Yeah? Sorry. Am I right? No, sorry. When you do a torsional test, what do you get? You get a Mohr circle centered at the origin here, right? Centered at origin. Okay? Because when you do a pure shear test, a torsional test, and that's the Mohr circle you have, centered at the origin. And then you can do a pure compressive test. So you will get a Mohr circle which will be purely on the left side here, right? And the tangent, they're both tangent here. So that's 3 circles here, right? It's basically any material you can get 3 circles like that. Then the Mohr theory basically saying is, okay, maybe I can connect the boundary, okay? Connect the boundaries, right? From the 3 circles. Then within the boundaries, I have a safe region, right? Outside the boundary, I have unsafe region, right? That's actually makes absolute sense, right? Makes absolute sense. But the only challenge is you don't have the luxury of doing the test for every material. And you don't have the luxury, maybe sometimes it's actually not that easy to do a compressive test or not that easy to do a torsional test, right? Yeah. So then the problem is, what would the boundary look like, right? You know, you can't get an experimentally determine a boundary for every material, right? Is it going to be a quadratic curve, or is it going to be a straight line, or is it going to be something else, right? Yeah, so that's basically the challenge facing this Mss theory. Then the Coulomb guy, right, that came in the picture here. Okay, so let's do something simple, right? So the Coulomb thing is, forget about the middle one here. Let's just connect the two tangent lines based on the compressive and the tensile. Okay, so connect that using two straight lines. Okay, then the Coulomb thing is, now you started to do shear test, right? As long as the middle circle become tangent to this one, and then I would call that failure. Okay, so that's what the Brittle Coulomb, basically the Coulomb guys, the theory here. Okay, it's not perfect, but that's a hell of a approximation. Actually, it turned out to be okay in most cases. Okay, so basically the key point here, the Coulomb came out. The idea is the boundary here are two straight lines. So if we call this BD, this is a straight line. Okay, it's a straight line here. That's basically the key point. All right. Yeah. So the definition, more precisely for this BCM. Okay, BCM is, okay, failure occurs when Mss circle becomes tangent to line BD. Okay, when failure occurs when the Mss circle becomes tangent to the line BD. Okay, it's very simple. Okay, very simple. Was that good? Yeah. And where's the line BD from? The BD line are based on two Mss circles. One is the Tensile Test circle. The other is this compressive circle. Okay, Mss circle. Okay, yeah. So the whole question is, what will be the mathematical expression here? I'm running out of time here, so I'm going to skip some derivations here. Okay, so I have a pretty detailed derivations of each one of the theory, but I'll summarize as to basically different cases as to what the BCM is according to this general definition. Okay, general definition. Any questions? All good? Does assignment need a brittle material? I don't remember now. Did you see any brittle material theories in assignments? If not, then we're good. Yeah. No? Okay, that's good. So yeah, we only have two theories left, but it's pretty simple. Okay? Yeah, good. Watch the Connect. Sometimes I post some video helps on assignments. Okay, and I'll try to record lecture videos too. Okay.